Okay, welcome to Unit 5, Lecture 4. We're going to talk about the law of conservation of energy. So you already know from experiencing things in your life and riding on a roller coaster and whatnot that energy can change from one form to another. Right? But this is going to introduce this idea that only energy changes, but the total amount of energy does not change. Okay. So we never can destroy energy. This is the basic concept we're going to kind of run through today. Okay, so let's talk about a hair dryer. Right, maybe one of your parents uses it to get ready in the morning, but when you plug in a hair dryer, you're starting with electrical energy. Okay, you're starting with current or electricity, electrons traveling through that wire. So it begins as electrical energy, right? Travels along this wire and then goes into the machine, the hair dryer. And in the hair dryer turns to three forms of energy. Okay, it transforms into thermal energy. Kind of that's the most kind of prevalent, right? That's the heat coming from the hair dryer. It turns into kinetic energy. You've got a fan in here turning, right, and that's moving the air through it. So that's anything that moves is kinetic energy. And obviously it's super loud, so it makes a lot of sound. So it transfers to sound energy. So within this little system right here between the air, the hair dryer, and the electrical outlet, you've got a transfer of energy. Okay, so it's all the same amount of energy. Okay, we kind of call that the sum, total amount of energy. The entire time, it just changes from one form to another. So this is the law. This principle is recognized as a law. It's called the conservation of energy, the law of conservation of energy. It states that energy cannot be created or destroyed. All right, so since the Big Bang here, since we have the creation of all matter expanding outward in every single direction, right, in the universe, we have had the same amount of energy in this system, which we'll call the universe. We've had the same amount of energy there the whole time, right? It's all just changed from one form to another, maybe from heat to kinetic energy to potential energy in the form of stored energy and rocks and minerals and things like that, but it's all just the same amount of energy transformed from one form to another. So you might think about the idea of conservation in terms of conserving, right? So the law of conservation of energy is a little bit different from that, right? So it's not just keeping or reducing the amount of energy used. It's a universal principle that describes what happens to energy as it's transformed from one object to another as it's transformed, okay? So as it goes from, let's say, kinetic to potential, the total is conserved, okay? So the total amount of energy is conserved, not one particular type, or the total amount in the system is conserved, all right? So I think when we think about maybe the word conservation or conserving, we think about turning the lights off, using maybe a hybrid car that conserves fuel. We think about using less, right? So we're not exactly talking about using less. We're talking about there being no reduction, right, in the law and in terms of a system, in terms of energy. All right, so let's get into more specifics around energy transformations. So you're more likely to think of energy as race cars roaring past, or as your body uses energy from food to help it move, or the sun warming your skin on a summer day. All right, so those are common forms of energy transformation, right? You feeling the warmth, you getting the energy from food. These all involve energy changing from one form to another. So to the food example, chemical energy stored in the food and the beef and the cheese and the special sauce and all that stuff on the hamburger are transferred into chemical energy in your body, right? So stored as fat, especially with something like a cheeseburger. Burned right away in terms of thermal energy, right, to keep our bodies warm, and then or used to move, or to have your heart beat, or to have your lungs expand. That would be mechanical energy. We'll talk more about that in a minute. Mechanical energy is the sum or the total of kinetic energy and potential energy of the objects in the system. Often the mechanical energy of a system remains constant or nearly constant. In these cases, energy is only converted between different forms of mechanical energy. So that roller coaster, we'll talk about it again here, is a good example of that. Up here, it's got potential energy, right? It's got, let's say, I don't know, 1,000 joules of potential energy as it travels down the track. That gets converted to kinetic energy. All right, and then as it reaches the bottom, potential again. Okay, now this entire time, this entire energy transformation, the same amount of energy is in that system. Okay, so we will call the combination of the potential energy and the kinetic energy mechanical energy. So falling objects are an easy system to understand. Apple Earth system on a tree has gravitational potential energy due to the gravitational force, right, pulling down, that downward force. The instant the apple falls, comes loose from the tree, it accelerates due to gravity, right? So its kinetic energy increases here. Right? As the apple falls, it loses height. So the GPE, the gravitational potential energy, decreases, right? So it's at its max GPE here. Gravitational potential energy here. And as it falls, so does the gravitational potential energy. So as it falls to the ground, the GPE declines. All right, this potential energy is transformed as it falls to kinetic energy. The potential energy that the apple loses is gained back as kinetic energy. All right, so as it falls, it becomes kinetic energy, and thus the energy is conserved. Right, it doesn't disappear; it just turns into something else. Projectile motion is another way to think about this. Right, so even when you strike a ball, the ball initially has a high kinetic energy, low potential energy. Up here, it's got its max potential energy, and as it falls again, more kinetic, and finally zero potential energy as it reaches the ground again. Okay, so you can see in the curved path, similar to how a pendulum swings. We'll talk about a swing in a second. This swinging back and forth between potential and kinetic. Energy transformations again involve mechanical energy, because mechanical energy is the combination of both potential and kinetic energy. Okay, so all the way through the contact of the ball, the arc of the ball, the entire projectile motion, that mechanical energy stays the same, right? Because since it's the sum of the kinetic energy and potential energy, we're just seeing, one value go up and one value go down as it moves through its path. So again, a swing. So we've all been on a swing before. You can feel being at the highest point up here and kind of the standing position here. There's that difference in motion, right? So kinetic energy changes again to gravitational potential energy. You're at your highest point up here, all right? And the lowest point of potential energy here at the bottom of the swing. So it's just like how a pendulum swings. We're seeing that constant transfer, so from kinetic to potential and back. All right, so there's other things in there. The system's not as simple as just potential energy and kinetic energy, right? There's other places energy goes, all right? So think about it like this. When you're coasting along a flat road on a bike, you know that you'll eventually come to a stop, right? So what stopped you? The tire was touching the ground, right? There has to be some friction there. So if the energy is conserved, why wouldn't your kinetic energy stay constant? Why wouldn't you just coast forever, right? If the energy is going to stay the same, well, we know friction opposes motion, right? So friction is a force that's going to oppose whatever motion you have along the surface. So we have to account for that. So let's go back to the swing again. All right. So if you don't continuously pump your legs, right, or have someone push you, your swing arcs are back and forth and back and forth. Those arcs are eventually going to stop, right? You're going to stop swinging, right? And what causes that? It's friction. Okay. In other words, mechanical energy of the swing decreases over time. All right. So as if the energy was being destroyed, but that can't happen, right? Because the law says energy cannot be created or destroyed. So with every movement, the swing's ropes rub on their hooks. So the hooks are right up here. There's a little bit of friction. If you touch that, it'll feel warm due to the friction. Okay. And we also have air resistance pushing on the rider. So friction and air resistance cause some mechanical energy to turn to thermal energy. So it's not a lot, but the air right around the swing set would warm up just a little bit. Okay, another way to think about this is a light bulb. So light bulbs, again, transform electrical energy to light so you can see. Now there's also a little bit of warmth produced, right, from that transformation. The older light bulbs, the light bulbs that are kind of shaped like that, the older style ones, I think I've talked about them in class a little bit, those incandescent light bulbs. Those light bulbs produce a lot more heat than I'd say that this newer CFL would, mainly because it's just less efficient. But anyway, we do still have this sort of byproduct again. So the total amount of energy coming from the plug, the electricity, a little bit goes to heat. Most goes to the light, the intended function, but we do have some of that, in air quotes, lost to heat. But of course, it's not really lost because that's a violation of the law, and you always think about that law in any system. A really common system that physicists talk about or use to talk about this concept is a car and a combustion engine. So in a combustion engine, you burn fuel. So fuel stores chemical potential energy. The engine transforms the chemical potential energy of gasoline molecules into kinetic energy of a moving car or bus. So in that car, you have a spark plug. There's your spark plug right up there. It fires, right? It creates a little spark, and it initiates that burning, the combustion of the chemical potential energy to thermal energy, right? As the hot gases expand, the thermal energy is converted to kinetic energy, right? So the pistons pump back and forth, up and down, and that's what turns the axle that moves your car, all right? So as you hit that accelerator, you are burning the gasoline or the diesel fuel, and that fuel eventually turns to kinetic energy, right, as the car moves forward. Okay, and then we'll kind of finish here talking about chemical energy. We'll kind of go back to the food example. Some energy transformations are less obvious because you can't see, a car moving or feel the heat from a light bulb, but every plant also does energy transformation. So that radiant energy coming from the sun, right, we're going to call that radiant energy, gives plant the energy to convert that to food, right? And the rate at which energy is converted is power. We've talked about power briefly already, but we'll kind of think about it a little bit different, a little more broadly here. So what power really is the rate at which energy is converted. All right, we're going to measure power in watts. That's a capital W. And 1 watt equals 1 joule per second. Okay, and the formula down below, we looked at it before, kind of like work over time, and that's still accurate. But more broadly, when you're thinking just about energy itself, it's how energy is used over time. So E being energy over time is the formula for power. All right, so doing things faster is called doing with more power or having more power in the system, right? So power tools allow you to complete work faster. Think about your power screwdriver. Maybe your dad's got that, or your mom. That's a great drawing, by the way. That would do a job much faster. That was supposed to be a screw, as opposed to your handheld screwdriver that requires you to turn the screwdriver with your hand, right? You're going to do it much faster with the power tool because the time's going to be much lower. Okay. And back to the human body here. What kind of energy do we have in the body? We've already talked about heat a little bit. But as you move up your right hand, reach up and you feel your shoulder, you are converting potential energy from your body to kinetic energy. So that potential energy is already in your body from your breakfast or your lunch last night or yesterday or your dinner you had. You've already got that potential energy in your body. All right, and so some little examples here of how much energy we use with a few different actions here. So you sitting right now, if you're like a medium-sized guy, you sitting listening to this lecture, you're using 84 calories an hour, and a calorie is just another unit that you can kind of use to replace joules. Obviously, if you use more kinetic energy, you're going to burn more calories, right? So running would use more calories than bicycling or playing tennis. Even when you sleep, you are using calories per hour. All right, so just a review of the big idea here. Energy is converted between many forms, right? You can take any form of energy and convert it to another. Okay, you can take mechanical energy and convert that to electricity, right? You can ride one of those bicycles and power a light bulb. You can change thermal energy to electricity. You can change chemical energy to any one of those things. And again, the law of conservation of energy states that energy can never be created or destroyed. The total amount of energy in the universe is constant. So it's a really important idea when you're thinking about balancing any kind of equation within the system. You always have to account for the sum total of energy. It has to be a constant. You can't lose any energy. Where does that energy go? All right, if you're going to be an engineer, you're designing a machine, you have to account for that, right? You have to figure out where that energy is going to go and if that's going to harm the efficiency of the machine. So hopefully this was a little helpful, and you can answer some questions on the law of conservation of energy tomorrow in class. Hope you have a good day, and take care. Go Bills.